Cool. So welcome back, everybody. And it's a real pleasure to introduce Sefi Naor. Sefi is a professor at the Computer Science Department at the Technion in Haifa. He's done a lot of beautiful work in algorithms, a wide range of topics, but his recent interests have been in online algorithms, and he with his student Neve Bookbinder have been responsible for the revival of online algorithms in some sense, with the introduction of the primal dual technique, of which he'll talk more about today in his talk on online rounding of bipartite matchings. All yours.
Right. Thanks very much, Anupam, and thanks for inviting me to the workshop, and thank you for the organizers. So I'm going to talk about online rounding of bipartite matching, and actually it's going to be I'll talk about two papers with written with Neve Bookbinder, Arvind Srinivasan, and David Weitz. So let's start with a basic bipartite online matching. I'm sure you're all familiar with. We have a bipartite graph. One side is the offline vertices, and this side is known in advance. And now the online vertices come one by one. Arrives, we're unable to match it. So we can only get the online matching has only two edges, while the optimal algorithm can match four green edges. So our competitive ratio is defined to be the ratio between the number of edges that alg matches versus opt. This problem was introduced more than 30 years ago by Karp, Vazirani, and Vazirani. It has become a very fundamental problem in online algorithms. Half what we've just seen is best possible online. And the very interesting result of KVV is that a randomized algorithm can get a competitive factor of 1 minus 1 over E. And using a very simple idea, we first pick a random permutation of the offline vertices and then run a greedy algorithm according to the priorities defined by the random permutation. This basic model has been generalized to the vertex-weighted case, edge-weighted, and what's called the AdWords problem. For these two problems, the 1 minus 1 over E currently is only known to apply to the fractional version of the problem. I'll explain what that is. And recently, the basic deterministic competitive ratio of 1/2 has been broken for edge-weighted matching. This is edge-weighted with free disposal. Without the free disposal, which allows us to dispose of previously matched edges, one cannot get any finite bound. And also for AdWords, the 1/2 has been broken recently, but the known randomized bounds are still between 1/2 and 1 minus 1 over E. What's a fractional algorithm? So in a fractional algorithm, when a vertex arrives, we can match it fractionally to the offline vertices as long as the sum of the fractions adjacent to the vertices in the graph is not more than 1/2. So this is the fractional relaxation. This is the polytope, which is defined by the fractional relaxation. So the sum of the x's adjacent to any vertex is at most 1. So this is just an example of a fractional solution, and in this example, the algorithm is capable of getting 3.2, and opt is still 4. Let's look at this at this fractional relaxation, at this polytope, what properties does it have? Well, first, no, I mean, this is the well-known property. This LP relaxation is an integral. So the integral opt is equal to the fractional opt. Now, suppose we're given a fractional point in this polytope, then we can turn it into an integral point, which has the same value or even more, meaning number of matched edges, and the probability of an edge belonging to the matching is equal to its fractional value. And this means that any linear objective is preserved in expectation. We can call it lossless rounding. Now, in general, this is a very nice property. It can be useful in fairness, for example. If we could have this property in the online setting, then we might be able to get a 1 minus 1 over E competitive factor for online edge-weighted matching, which I mentioned before. This is an open problem. Has been open in online computation for many years. Whether we can get this bound online. Okay, so let's focus on lossless online rounding. So suppose we have 4 offline vertices. Now the first online guy comes and we just give fraction of 1/2 to each of the 2 edges. Okay, this means that we need to round, if we want to get lossless rounding, then we need to pick each one of the 2 edges with probability 1/2. Let's say we picked the red edge. Now comes T2, same thing. We attach fractions of 1/2 to the 2 edges, do the rounding, and pick the red edge. So the probability that each of T1 and T2 are matched is 1/2 plus 1/2 equal to 1. Now for each one of them. Now let's look at the 4 pairs from the Cartesian product 1, 2, and 3, 4. So 1, 3, 1, 4, 2, 4, 2, 2, 3. And now let at least one of them must have, since the 2 vertices, T1 and T2 were matched, at least one of them has, of these pairs, has probability 1/4 of being matched. So in our, the adversary will when he brings in T3 will be adjacent to this pair, which has probability at least 1/4. So this means that the probability that T3 is going to be matched is at most 3/4 randomly, while fractionally we can give the value of 1/2 to each of the 2 edges that are adjacent to T3. So this example shows that lossless in general, lossless rounding is impossible. Now, what is the lesson that we can learn from this example? We want to get lossless rounding. In general, this is impossible. Now, what do we learn from this? So let me take a 1-second pause. So the result that I'm going to talk now about lossless rounding is from a paper that will appear in SOTA 23. And when I finish presenting this, I'll talk about another aspect of online rounding, which is in a different paper. The common thing is to the two papers is one of the authors. Okay, so let's talk about lossless rounding. And one very simple observation is that any randomized algorithm implies a fractional algorithm by defining the fractional value, let's say, of edge E to be the probability that it's going to be matched by algorithm A. And that's going to give us a fractional algorithm which has the same competitive ratio. And if A prime is this fractional algorithm which is implied by algorithm A, then we can do trivially a lossless rounding of A prime by just running A. But can we do the converse, the inverse direction, and add constraints that will make the online algorithm have this lossless rounding property. The problem with the example that we saw before, in a sense, the fractional online algorithm is just too good. It just gives you too good a matching. And in certain cases, so we know that in the worst case, the competitive ratio of the fractional algorithm is 1 minus 1 over E. But in certain cases, in certain instances, the fractional algorithm achieves a much better bound than 1 minus 1 over E. And this bound is, and for these instances, integrally, a randomized integral algorithm just cannot achieve that competitive factor. And this is the source of trouble, why we cannot, in general, why we cannot do lossless rounding. So this means that in a sense, we need to take our fractional algorithm and make its performance is too good, and we need to make it slightly worse. But how do we do that? What constraints can we add to the fractional matching that would make it into a lossless solution, lossless rounding, have the lossless rounding solution? Okay, so we're going to focus on what's called two-choice algorithms, which means that an online algorithm only considers two of its offline neighbors and changes the fractions of these neighbors. Now, in general, two-choice solutions are not losslessly roundable. This is what we saw in the bad example. So this means that we need to add more constraints. By the way, two-choice algorithms have been previously used in the breakthroughs. Oops. Yeah, in the breakthroughs for weighted matching and for AdWords. In both examples, the deterministic factor of 1/2, which was took many years to break it, it was broken using these two-choice algorithms. Okay, so the idea is we're going to add a constraint, a nonlinear constraint, which would help us in lossless rounding. So let's look at this online vertex T, which is adjacent to offline vertices 1 and T with fractions x1t and x2t. Now, the probability, if we have lossless rounding, the probability that t is matched is equal to x1t plus x2t. Now, by the same token, the probability that t is matched at a time earlier than t, sorry, I is matched, no, it should be, okay, the vertex is each of the vertices 1 and 2 are matched before time t is just the sum of the fractions which are adjacent to them. So the probability that t is matched cannot be more than 1 minus the probability that 1 and 2 were matched earlier than the arrival of t. So if these guys are in the events that 1 and 2 are matched, these events are independent, then we just get that the following constraint, x1t plus x2t cannot be more than 1 minus the product of the events that these two guys, 1 and 2, were matched before t. And actually, this should even hold when we have negative correlation dependence between 1 and 2. Yeah. So this is our basic constraint that we want to add to the online fractional algorithm. And the idea is that if we can maintain this constraint plus pairwise negative correlation, then this is sufficient for first matching with the correct marginal probabilities, meaning lossless rounding, and maintaining this negative correlation for subsequent steps. And this is basically what we're doing. We match with the right probabilities and maintain negative correlation, and this way we achieve lossless rounding. And as a result, we get, I won't get into the precise details of the algorithm, but we get a bound of 0.536, which is better than 1/2 competitive two-choice algorithm, and which maintain this new constraint. One nice application of this work is to what's called the advice model in online algorithms. So in the advice model, the online algorithm gets a non-deterministic string which it can use for making its decisions. So for example, in online matching, if we get a string of length n log n, then we could encode the offline matching in this string. So one question that was asked is what is the minimum number of bits of this advice that is needed to get beyond the deterministic 1/2 that's known. And in work by Pena and Borodin from a few years back, they showed that this lower bound is log n. And in terms of upper bounds, log n advice bits were known using exponential time or linear with polynomial time. Now, a randomized algorithm is a special type of, a special case of a non-deterministic advice, of course. And turns out that our two-choice algorithm can be implemented with only constant, with random variables which are constant-wise independent for some constant. And using epsilon bias distributions, these we can generate almost constant-wise random variables using only log n bits. So the lower bound of Penna and Borodin is matched by an upper bound of a randomized algorithm. Another open question, of course, is first of all, can we get 1 minus 1 over e with lossless rounding? So one natural approach would be take this constraint, this new constraint, generalize it from two choice to any choice. Unfortunately, this is not enough. We can show that fractionally, when we generalize this constraint, we can get a 1 minus 1 over e competitive factor, but unfortunately, we don't know how to round this. It's actually impossible to round the fractional solution obtained this way. Something more is needed. I don't know what this extra thing is, but it would be very interesting, of course, to get 1 minus 1 over e, which would hopefully be applicable also for the weighted case. So let me now change gears and look at online rounding of matching from a different perspective. So now forget about lossless rounding. Now we're in the world of lossy rounding. And let's say that our input is a bipartite graph, as before, where one side is known in advance, and the other side is exposed one vertex at a time. However, this time we also, together with the edges which are exposed to us, we also get the fractional solution. We can think of the fractional solution as, for example, predictions. And now we need to, upon arrival of an online vertex with the fractional values that are attached to the edges adjacent to it, we need to round the new edges, and we want to lose as little as possible, meaning that for every new edge that arrives, the probability that that edge is going to be added to the matching is at least alpha times xe, the fraction that we received for edge e, and we want to maximize alpha. This problem has been looked at, and alpha is known to be at least 0.526 for simple matchings. We show first a hardness of 0.828 in our work. This is the best alpha that upper bound on alpha, and our main result is we go beyond 1 minus 1 over e. So 1 minus 1 over e is like a magic number which appears a lot in competitive factors of online algorithms, especially for matching. So for this specific problem, we can go beyond 1 minus 1 over e by some small constant. And and this is actually achievable for B matching. So B matching is when you're allowed to, for every vertex is allowed to be adjacent to no more than B, vertex V, no more than B of V edges. Simple matching is just when B is equal to 1 everywhere. So let's start with a case Um, let's start with a case where we have only one offline vertex and many online vertices which appear one by one, and we're looking at the the online vertices appear one by one. So this is our offline vertex I, and we have the neighbors 1, 2, etc. appear one by one. And when we do the matching, we would like to have the prefix property, which says that when at time t, when online vertex t has arrived, the number of matched edges is between the floor and the ceiling of the fractions sigma xij, where j runs between 1 and t. Okay, so let's say the fractional degree just before the arrival of time t, let's call it dit. So we can actually, for this special case, we can actually get lossless rounding. So when t arrives, we basically, if I is still free, meaning it has not reached its capacity of b, then, and this has happened inductively with probability 1 minus dit, we want to match the new online vertex t with probability xat divided by 1 minus dit. And this is a bit simplistic because we have to also make sure that the prefix property is maintained. I won't go into the details, but it turns out that the online algorithm that we have has the same distribution as previously devised offline algorithm by Arvind Srinivasan. And we can also get concentration and, of course, the prefix property that I mentioned before. Okay, so we've nailed down the case of a single offline vertex. This is also called actually online level set. And now we're going to use it when dealing with a general bipartite graph. So, so the algorithm is the following. Each offline node I is going to see online neighbors which arrive one by one. So let's say we are at time t. Each one of the offline vertices independently is going to run the single offline vertex subroutine that we had just seen. So let's call let AIT denote the event that when I ran the level set algorithm for a single offline, AIT is equal to 1 means that I is supposed to be matched to the new guy T. Now, of course, the issue is that each one of them is each offline vertex runs its own independent copy of the single case, and there may be more than one guy who is offline guy who is supposed to be matched to T. And we call this set of proposers, it's a random set, we call, this is the set of proposers to online vertex T. And we're going to pick one of them and from one of the nodes in PT and match it to T. And I'll discuss how we do it in a minute. So this is the basic algorithm. So one immediate observation is, of course, if you believe the last line matching to a single node from PT, then the matching constraints are satisfied. I'm now restricting the discussion to matching, not to B matching. The extensions to B matchings are not difficult. And the second observation is that if we look at any subset S of offline vertices, then by independence, each one of them is running the single offline vertex procedure independently. So the probability that the intersection between S and PT is this intersection is not empty is equal to 1 minus the product of 1 minus xit. Now remember, the case of a single offline vertex is lossless. So each edge it for each I is going to be picked with probability xit. So the probability that the intersection with S is non-empty is 1 minus the product of 1 minus xit. So we have this property, and I will first show you that this implies a 1 minus 1 over E rounding ratio, that alpha is equal to 1 minus 1 over E. And actually, we will see that we can get better than 1 minus 1 over E if one of the fractions is large. And if one of the fractions is not large, then we will force it to be large and get it for any x values better than 1 minus 1 over E. Okay, so first observation is that the probability that the intersection is non-empty is, at least by just standard inequalities, is at least 1 minus 1 over E times the sum of the fractions. Now, when is this the sequence of inequalities, when is it tight? So it's tight when all the x's are small. Okay, so we'll deal with that in a minute, but let's see what we can, meantime, what we can still obtain, even if the fractions are small. Okay, so we have this inequality, and the question is, can we get the 1 minus 1 over E? So we want to pick a single offline node from the random set PT, so that for each I, the probability that IT is in the matching is equal to the expression on the right hand side, which is at least 1 minus 1 over E times xit. So it follows from this earlier work of Feige Vondrak and Bansal and Ilan Cohen that we can get 1 minus 1 over E. So let me quickly show you how we can do that. And basically what we need to do is provide a formula, a way of computing the conditional probabilities on all possible choices of the set PT. So we construct a flow network. On the left-hand side, we have all possible choices of offline subsets. And on the right side, we have the offline nodes. The offline nodes go into T with capacity alpha times X xit. Alpha now is 1 minus 1 over e. And the capacity from the source into the all possible choices of offline subsets is just the probability that PT is equal to the to subset AI. Now, let's pick some subset S of offline nodes, and which offline subsets feed into it? Well, all those subsets whose intersection with S is non-empty. Now, we know that, well, if we look at the sum of the probabilities that PT is equal to A, that's exactly the probability that PT intersect with S is non-empty, which we have already shown is at least alpha times the sum of the xit's. So what we get is that Hall's condition is satisfied for S. So S can has enough capacity to satisfy Hall's condition with a scalar alpha of 1 minus 1 over e. And given a flow solution, we can define the conditional probability that edge IT is picked to the matching, given that PT is a specific subset A. It's just the flow from A into I, divided by this probability that PT is equal to A. So this gives us a general procedure for picking one offline vertex for a given alpha. Now, currently, I mean, up to now, the only alpha that we can guarantee is 1 minus 1 over e. Now, the question is, how can we increase the value of alpha and then run this procedure to pick one of the proposers? Okay, so the tight example, we said that when the fractions are small, we have a problem. Let's say xit is just 1 over n for n vertices. Then, of course, if we just do independent sampling, we get 1 minus 1 over e, which is tight. Now, of course, in this example, we can run a dependent rounding where we pick one of the offline vertices uniformly at random, and then alpha would be equal to 1. That by itself is not very interesting, but it hints to which direction we should be going to get alpha to be bigger than 1 minus 1 over e. And the idea is we're going to aggregate. This is actually what we did in the example with a 1 over, when everybody was 1 over n. Instead of treating them as separate entities and picking independently from them, we just aggregated them together and then picked one of them. So this is the basic idea. We'll take the proposers and we'll just pack them together where each proposer has size probability of xit divided by 1 minus dit. Dit is just the fractional value from before, or the probability by which that guy has already been matched. The problem is that the sum of the p's can be strictly bigger than 1. Then what do we do? So instead of just aggregating them together, we'll just bucket them in several bins, and we will think of each bin as a single guy. We'll pick from the bin, and this is how we will force the existence of one big fraction and get beyond 1 minus 1 over e. So we'll just run first fit on the size on the offline vertices, where each guy has size xit divided by 1 minus dit. So here's a simple example. We're running first fit. And so we get a distribution into bins. From each bin, we'll just sample by picking a uniformly chosen threshold between 0 and 1, and that will determine the precise variable offline vertex that we're choosing from that bin. And first fit has a nice property that it guarantees that all bins except for one are at least half full. I'll be done in 2 minutes. Okay, so the probability of getting a proposal from a bucket is just equal to the sum of the fractions in the bucket. And if all the d's are small, then we're going to get the sum of all the x's where d is small, let's say less than half. If this sum is large, then we're going to get a large item. Another nice property is that the buckets behave nicely, almost independent, actually negatively correlated, which is exactly what we need. And this implies better than 1 minus 1 over e if the sum of the x's of the low degree, those for which d is small, if this sum is large. If that's not the case, then we have to do something more complicated, which we call borrowing from the past. And we have to play with the low degree offline vertices and the high degree offline vertices and rescale them. The smaller one decrease and the higher one increase. I won't go into the details, but the bottom line is that we can force the existence of a large fraction in practice and get alpha to be bigger than 1 minus 1 over e, and now we can run the flow procedure that we saw before and get a randomized algorithm whose loss is this value alpha. Some quick applications, so it improves on several results, known results. For example, online edge coloring of multigraphs. The issue there turns out to be exactly B matching that we considered in this work, and also online stochastic matching. We get 1 minus 1 over e was not exactly known before. In any case, we get better than 1 minus 1 over e. And just to conclude with open questions, so we want to better understand online rounding of matchings. I already discussed in the case of lossless rounding, we want to go beyond two-choice algorithms. And one motivation is online edge-weighted matching with free disposal. For lossy rounding, well, we got better than 1 minus 1 over e, but still the gap between the bound that we have and the hardness bound of 0.8828 is still large, and we'd like to solve this gap. And of course, go beyond bipartite matching. So I'll stop at this point and happy to answer questions. Yeah.
In the first part of your presentation, you had a new set of constraints to describe an online algorithm, right? But they were very non-convex constraints.
They were very what?
Non-convex constraints, right? So how do you solve this? How do you analyze this?
Okay, that's a very good question. So the thing is, I don't need, they are non-linear, non-convex in the offline version. When I do the online thing, when I reach online vertex t, then I already know the previous values x, and so it becomes a linear constraint. And actually, what we do is some kind of a water level with this extra constraint. So water level is the way you would do fractional matching and get a solution that cannot be rounded. When we add this constraint to the water level algorithm, then we can do the lossless round. Thank you.